Okay, so I thought we'd talk today about voltage sources and Thevenin's theorem. The first thing we want to try to understand, or at least review, is what a voltage source is and how it behaves. Obviously, there are going to be no true voltage sources in the real world, but we'll start with a true voltage source as a construct and then try to describe what we might actually see. So, in a true voltage source, as we draw it, we'll connect it to a resistor here. And let's say this is a 5-volt DC voltage source. Now, based on what R is here, we're going to get a current that flows around our loop here. And a current from Ohm's law is going to be, remember our mnemonic over here, we had V over IR, like that. And if we want this current, I total, we would say I total equals, we're trying to solve for I, so it would be V over R. So I total is equal to V over R, and in this case it would be 5 volts divided by R ohms. So let's look at case 1. R equals 1 ohm. Well, in that case, I total is going to equal V over R equals 5 volts over 1 ohm, and it's going to equal 5 amps. So in order to make that true, I'd have to have a power supply that's capable of delivering 5 amps to that load of 1 ohm. And let's say R equals 50 ohms. That's a common load in RF and instrument systems, in which case I total would be equal to 5 volts over 50 ohms. And we could say that's equal to 0.1 ampere. If we work that out with scientific or engineering notation rather, we would see that it's equal to 100 milliamperes, because 1 ampere is 1,000 milliamperes, milliampere being 1,000th of an ampere. Yeah, so that's all well and good. Let's take an extreme case. Let's take the case where R is equal to 0.001 ohms. R is equal to 1 milliohm, if you will. Well, I total equals 5 volts divided by 0.001 ohm, and we can bring in the engineering notation here. We have 5 times 10 to the 0 volts divided by 1 times 10. And what is this? I took the decimal point from here and I made this bigger by 1,000. 1, 2, 3. So I've got to make this number smaller by 1,000. Okay. And what we find is that we have 5 divided by 1 is 5 times 10 to the 0 minus negative 3 amperes. And that's going to be equal to, well, we have minus and negative as a positive. So I'm going to wind up here with 5 1,000 amperes equals 5 kiloamperes. That's a lot of current. But the point is, mathematically, if this is a voltage source, it's supposed to be able to deliver whatever resistive load we have, or whatever kind of load we have out there. This is going to make this voltage across this resistor is going to be 5 volts. That's it. That's what a voltage source is. If this were a sinusoidal generator and it was a voltage source, then no matter what resistor we had, we'd have a sine wave that respected Ohm's law and supplied the total current. I'm going to move my paper up here a little bit here. Now let's talk about real world voltage sources, if you will. Real world voltage sources have an internal resistance. So a real world voltage source, we can imagine it as containing an ideal voltage source, but also having a series resistance. This resistance, we can call it maybe R internal or RS for series, and here's our voltage source. So we can call this VS if you like, and maybe this will be 5 volts in this case. And we can then kind of draw a box around this thing. If you will. And this is our real world voltage source. And we can characterize it by in a couple ways. We can connect it to a load of R ohms, or why don't we call it RL as our load. And we know that the terminal voltage, the voltage across RL, can be solved in this circuit by certainly applying the total resistance method. We have our R total is going to equal R internal plus RL. Our total current, therefore, in this case, is going to be VS over R internal plus RL. Okay, and of course, in our case, that's going to be 5 volts over R internal plus RL. And the terminal voltage here, we're going to call this voltage VRL, is called terminal voltage. It's the voltage we see across the terminals. So in our case, the terminal voltage, VRL, is going to be equal to I total times RL. And this is just another recapitulation of what some people call the voltage divider rule, but that says VRL is going to be equal to, here's I total right here. So it's going to be equal to VS times RL over R internal plus RL, and we know that VS is 5 volts, so I guess we can say 5 volts times RL over R internal plus RL. Now, we can kind of look at this expression right here. Let's sort of put that in a box, if you will. So if RL is a huge number, okay, so if RL is much, much greater than R int, then this number RL over R int plus RL, the R int won't matter, and this number will be close to 1. So RL over R int plus RL, that'll tend to get close to RL over RL, which equals 1, in which case VRL will just equal 5 volts. 5 volts times that. And so this is also true. You could also say if R int is much, much smaller than RL, or RL is much, much greater than R int. It's not an or so much as it's the same thing. But the point is, if this internal resistance is really small compared to the load resistance, or the load, if you look at the other way, if the load resistance is much, much larger compared to the internal resistance, then we're going to see a voltage out here as the terminal voltage that's going to be very close to VS. Okay. Now in the other case, we're going to see a voltage out here that is determined by the voltage divider rule, because we have a voltage divider here. We have an internal resistance and an external resistance, which is our load resistor. And so, internally we might know this is 5 volts, but we probably should measure what our output actually is in order to see, what's going to be the case for current delivered to our load. So there's the formula that once you know those two things, and this is VS. If you don't know, if for any other problem other than 5 volts, we're going to stick in the VS there, our load resistor and our internal resistor. So this is a real compact form of looking at a real world voltage source. And in reality, if we were talking in, say, the steady state AC case, yeah, there could be capacitance and inductance and all that stuff, but that could all be kind of lumped into a reactance that sits right there in series. All right, and we're not going to go through that kind of detail, but that does actually happen. We may talk about cases where it happens and that sort of thing, but for now, let's just stay in the DC case and talk about what happens with real-world voltage sources in the resistive case. Okie doke. Thanks a lot, and we'll go a little farther in our next talk about this. Take it easy, and we'll see you soon.